High-concurrency architectures are susceptible to a specific class of failure, the total silent freeze. A complex operation processing millions of instructions per second simply stops. Here, thread 1 secures the first mutex, and thread 2 secures the second. When each requests the other's locked mutex, both halt indefinitely in a circular dependency. This is deadlock. All threads are blocked, waiting for resources held by another thread in the set. This differs from a live lock. In a live lock, threads continuously consume CPU cycles changing states without making progress, like two people repeatedly dodging into each other's path in a narrow hallway. A deadlocked thread consumes 0 CPU time. The execution state is static. These freezes are deterministic topological failures. Diagnosing them requires stripping away the source code and modeling the system's state space mathematically. Operating system theory defines a strict engineering law. A deadlock can only occur if 4 specific conditions exist in the system simultaneously. The first two are mutual exclusion, where a resource is inherently non-shareable, and hold and wait, where a thread retains its current resources while actively requesting new ones. The final two are no preemption, meaning the operating system cannot forcefully strip a resource from a thread, and a circular wait, a closed chain of thread dependencies. This is a resource allocation graph, the formal model used to map these 4 conditions. Active threads are circular nodes, and resources are square nodes. A request edge points from a thread to the resource it needs, while an assignment edge points from a resource to the thread currently holding it. Mapping code onto directed graphs transforms the abstract problem of resource contention into a visual dependency audit. If a cycle exists, the graph identifies exactly where the system state is failing. The primary diagnostic rule of the resource allocation graph is straightforward. If the directed graph contains 0 cycles, the system is mathematically guaranteed to be safe from deadlock. A circular wait manifests as a closed loop within the graph's geometry, shown here in red. With single-instance resources like standard mutex locks, a cycle indicates absolute deadlock. The threads are unable to transition to a new state. Multi-instance resources add a layer of complexity. This graph shows a cycle, but it features a resource type with multiple identical instances. One of these instances is held by thread 4, which sits outside the closed loop. In a multi-instance graph, a cycle only indicates the possibility of an unsafe state. If that external thread completes its work and releases its resource, it can shatter the loop and free the blocked threads. Identifying these topological cycles and checking for available instances outside of them is the core diagnostic metric for evaluating system safety. In practice, operating systems like Linux and Windows often ignore deadlocks. Calculating the resource graph for every request is computationally expensive, so they rely on the ostrich approach, leaving deadlock management to application developers. Most developers use structural prevention. This involves architecting the software to ensure at least one of the 4 necessary conditions for deadlock can never be met. Lock ordering is the most common prevention strategy. All resources are assigned a strictly increasing numerical sequence. By forcing every thread to request locks in that exact order, a circular wait becomes geometrically impossible. While prevention limits how software can be written, dynamic avoidance allows the operating system to evaluate the safety of every resource request in real time. This chart maps the system's state space. A deadlocked state is always inside the unsafe boundary. An unsafe state isn't a guaranteed freeze. It simply means the operating system can no longer verify a sequence that allows all threads to finish. Avoidance algorithms block any request that would move the system into the unsafe zone. The banker's algorithm is the standard avoidance protocol. Threads declare maximum resource needs up front. Upon a request, the algorithm executes matrix math, simulating an allocation against the available pool. The request is granted only if the state remains mathematically safe. This creates a direct trade-off. Mission-critical systems gain absolute mathematical safety, but they pay a processing tax on every resource interaction. For systems that refuse the overhead of avoidance, but require more reliability than the ostrich approach, the strategy shifts to detection and recovery. Detection uses wait-for graphs, collapsing lines into direct thread-to-thread arrows. Databases run periodic sweeps to identify cycles. To recover, the system targets a victim node, aborts the transaction, and preempts all resources held by that thread. With the cycle broken, the remaining threads complete their work. The system then rolls back and reissues the transaction that was aborted. Managing deadlock is a fundamental requirement of concurrency. Whether relying on developer discipline, using bankers' matrices, or database rollbacks, systems engineering is a constant negotiation between maximizing throughput and the mathematical certainty of a system freeze.